Now, as we kind of get into a little bit more of quantum algorithms and start to approach the concept of quantum cryptography and the idea of communication and getting data from various qubits and the information that we are essentially transporting over the network, there are several items that we do need to keep in mind, one of them being a constructive and destructive interference. In order to have proper context in this, let's just briefly take a step back and you keep in mind that whenever we have some linear combination, whenever we represent the state, the superposition of some qubit of just any sort, we write it in the form d0, right, with some basis vector b0, right, plus d1 with some basis vector b1, right. In this case, d0 and d1 are what are referred to as probability amplitudes and amplitudes. And these probability amplitudes that we have here fundamentally are just referring to the chances of getting whenever we measure the spin of a particle, spin in the direction b0 or b1 in this case. Now, when we talk about probability amplitudes, again, the probability is expressed in terms of, say, the chances of getting measuring a b0, right? Spin in the direction b0 is equal to d0 squared, and the chances of measuring in the direction b1 is equal to d1 squared. And simply put, these are probability amplitudes. Alternatively, what you can say is that the probability is equal to the value of, your coefficients in this case squared. And what that means here is that your probabilities, right, cannot be negative. It doesn't make sense to flip a coin and have a negative 1/2 probability of getting heads. Quite clearly, this probability here has to be positive. But what is important to keep in mind is that whenever you square -1, right, that is equal to squaring +1. Which is always equal to 1. And what that's basically saying here is that while your probabilities cannot be less than 0, your probability amplitudes indeed can. And this is where the ideas of interference and whatnot come into play. And we'll approach that in half a moment. Now, in order to do so, however, let's really briefly let me remind you of the statement that whenever we have, say, spin measured in, say, the 270 and the 90-degree directions, what we're looking at is essentially something measured in the horizontal directions. And whenever we measure spin in the vertical directions, right, and if we attempt to take some spin measured in the horizontal direction and again measure in the vertical direction with spin in 0 and 180 degrees, we know that each of these have a 1/2 chance of occurring. This is quite straightforward. There's clearly nothing wrong with this. But let's say, on the other hand, we approach this problem with a slightly different linear combination, a slightly different vector, right? And let's say we have some vector v, some qubit, right? And we'll just name it v for convenience's sake. And let's say we can express it as a linear combination 1/√2 with spin to the left plus 1/√2 with spin to the right. And so what we have here is your standard vector, your standard linear combination. It's quite straightforward. Nothing seems to be wrong. Now, let's say we are measuring this in the horizontal direction currently. Now, if we want to switch over and measure things in the vertical direction, this is where things go a little bit strange, because if we measure it in the vertical direction, we can know that we get the spin and the direction up with absolute certainty. So let's interpret the vector that we have in front of us currently, right? Our probability amplitudes for both is 1/√2, and 1/√2 squared is equal to 1/2, meaning that whenever we measure the spin of the particle, we have a 1/2 chance of getting it to the 270-degree direction and 1/2 chance of getting it to the 90-degree direction. However, if we were to kind of translate this kind of basis and switch it over to measurement in the vertical direction, things get a little bit wonky. So if we were to, say, take it and multiply it out, right, and write in the essentially the vectors that we have in this case, 1/√2 and 1/√2 for spin to the left, plus 1/√2 multiplied by 1/√2, negative 1/√2, and you might recognize these vectors, right? This is basically the same thing, right? They correspond to one another. This can become a spin with 1, 0, plus 0, 0, 1. Now, as you may recall, actually spin in this direction corresponds to what is known as spin in the upwards direction. And here this corresponds to spin in the downwards direction, or 0 and 180-degree directions respectively. Right, and so what we see here is that when we switch the bases in which we're measuring it in, right, when we rewrite this linear combination as something else, what we have here is 100%, right, a 1 squared probability, essentially, of having a particle measured in spin up and a 0 chance of having it being measured in the spin down direction. And so what does this mean, right? If we put it in context again with the question of interference, what does this actually mean? And let me briefly rewrite what we had at the end right there. 1, 0, and 0, 0, 1. Right. What we end up having here is something that's quite curious, which is that here with our spin in the upwards direction, right? This is in the 0 degree direction, we have what is known as constructive interference. Its results are amplified in this case. And then for the spin in the 180 degree direction, it's known as destructive interference. That is, its results, its probability of being measured has basically been dampened in a sense. And so the idea here is that when we essentially develop quantum algorithms, we want to choose the linear combinations, the basis vectors, the orthonormal basis vectors that we're using exceedingly carefully, so the terms that we are not interested in end up being dampened, that they cancel, and those that we're interested in are indeed amplified, so we can get the proper information from them. And naturally, this is a brief just overview of things relating to the concept of probability, amplitudes, and interference, and how that affects, the importance of how we develop these algorithms as we kind of move forward, especially into, like, for instance, the very first topic, quantum cryptography, that is oftentimes, first broached a lot in computer science. Alright, if you have any questions, please do not hesitate to reach out or visit the Quantum Tech website. And as always, stay curious and keep on learning.